I would like to thank the organizers for this conference and for inviting me. I'm very pleased to give a talk here. So I will talk about geometric mitosis, and I will explain what it means. Originally, it's a term from biology, and it was introduced to mathematics by Knudsen and Miller. So let me start from some motivation coming, of course, from toric geometry. So in toric geometry, we have interplay between polytopes and varieties. So Newton polytopes encode information about geometry of toric varieties. And there are also polytopes in representation theory. For instance, Gelfand Zetlin polytopes and more generally string polytopes that were introduced by Bernstein-Zerevinsky and Littelmann. And it turns out that combining these representation theoretic polytopes and some ideas from toric geometry, well, sorry, I skipped one step. So recently, there was a huge generalization of theory of Newton polytopes, namely to any algebraic variety, one can assign not a polytope but a convex body, which sometimes is a polytope. And this convex body also encodes information about geometry of our variety. And this construction was developed independently by Kave and Khovansky and Zarsfeld and Mustata. And I'm going to talk about a more special case of this construction. Namely, I'm going to apply theory of Newton-Akunkov convex bodies to Fleck varieties. And there we get polytopes similar to string polytopes, but not necessarily string polytopes, as we will see. So what I'm going to talk about is how to do toric geometry on Fleck varieties. And the same ideas can be extended to more general varieties, such as spherical varieties, but I will only talk about Fleck varieties in my talk. So let me recall construction from toric geometry. So to every smooth projective toric variety, we can assign a convex polytope of the same dimension. So we have toric variety of complex dimension n, and the corresponding polytope has real dimension n. And geometry of the variety and combinatorics of the polytope are closely related. And in my talk, the following relation will be used. So faces of the polytope are in bijection with closures of torus orbits in X. So irreducible toric subvarieties in X are in one-to-one correspondence with faces of the polytope. And this allows to do intersection theory on polytopes, namely the intersection product of two orbits. Sorry, I should have taken closures of orbits here. So intersection product of two irreducible toric subvarieties is equal to the toric subvariety corresponding to the intersection of faces. And this is if faces are transverse. And if they are not transverse, there are certain relations between faces that allow you to make them transverse. So it's very similar to Chow rings. So if you have two algebraic cycles which do not intersect transverse, you can move one of them using some relations. And here's the same thing. And these ideas are allowed to give a very nice functorial presentation of a cohomology ring of a toric variety, which is due to Khovansky and Pukhlikov. Okay, so what can be extended to more general case? So suppose we have now just any projective variety, and then by the theory of Newton-Akunkov convex bodies, we can assign a convex body to this variety. And it depends not only on the variety and its projective embedding, but also on the choice of evaluation. So V is evaluation on the field of rational functions on X. I think Megumi and Kumers will say much more about this tomorrow, so I just mentioned that it's unlike Newton polytope, it doesn't depend only on the variety and its projective embedding, but also on evaluation. And different valuations might give you different convex bodies. And in many cases, this convex body is actually a polytope. And the main property of this convex body is that its volume gives you the degree of the variety X in this projective embedding. So it's similar to Kushnirenko theorem from toric geometry. So the degree of X is n factorial times the volume of P. And my question is there any useful relation between subvarieties of X and faces of P, assuming that P is a polytope. And of course, I want something like this relation between toric subvarieties and faces. Of course, it's a very, this question is not precise. So first of all, what kind of subvarieties one should consider? So for motivation, let me describe an example when this question is answered. So let X be the variety of complete flags in Cn, the one considered by Evgeny yesterday. So we take all flags of subspaces in Cn, and there are no gaps. So we have a line in the plane, in 3 space, and so on. And this can be generalized to arbitrary reductive groups. So this variety is GLN mod upper triangular matrices. And if one replaces GLN with arbitrary reductive group and take a Borel subgroup instead of upper triangular matrices, then we will get a complete flag variety for this reductive group. But right now, let us consider just flag varieties for GLN. Then there is a distinguished set of subvarieties, which are called Schubert subvarieties, and they give a basis in the cohomology ring. And they are defined as closures of Borel orbits, closures of the upper triangular subgroup in X, and have very transparent geometric meaning. So they are given by, so in order to describe a Schubert variety, you fix a flag in Cn, and then you measure dimensions of intersections of your moving flag with this fixed flag. So let me give an example. So suppose that n is equal to 3, so we are talking about Schubert subvarieties in 3-dimensional flag variety, GL3 mod B. Then we fixed a flag, so this black line and black dot is a fixed flag, and the moving flag is blue line and red dot. So we have one-dimensional Schubert subvariety, sorry, 0-dimensional Schubert subvariety. It's just a point. That means that our blue line coincides with fixed black line, and red dot coincides with black dot. Yeah, I haven't explained what is the relation between these pictures and the original definition. So for n equal to 3, we will have a line inside the plane inside a 3 space. But if we take projectivization of this, so instead of a vector line, we consider a point in P2, and instead of vector plane, we consider a line in P2, we will get exactly this picture. So we will get that our flag is just a line and a point in this line. And all this is in P2, in a projective plane. So this is a 0-dimensional Schubert cycle, and it corresponds to identity element of the symmetry group. So Schubert cycles, Schubert varieties are labeled by elements of the symmetry group. Then in order to get the Schubert cycle corresponding to S1, we should move a point inside the line. So the line is still fixed, but the red point is moved inside the line. So we get a Schubert one-dimensional Schubert subvariety. So now red point is anywhere on this line, but the line is fixed. In order to get the Schubert variety corresponding to S2, we should move the line without moving the point. So the point still coincides with black point, but the line is moved around. And in the same way, we get S1, S2, Schubert subvariety corresponding to S1, S2. So that means that we start from this one, and now we, so it's the matter in which order to multiply them. So we start from, so how, this one we can get from this one. Yeah, so we start from this one, and now we start to move the line. So we don't touch the point, we move the line around the point. We get this. And so on, and this is the biggest Schubert subvariety, which coincides with the whole flag variety. So we take flags which are in general position with a given fixed flag. And the closure of this, of course, is the whole flag variety. Okay, so here we have 6 Schubert cycles. And now we want to encode these Schubert cycles by faces of some polytope. And the good candidate for this is the classical Gelfand Zetlin polytope. So it is defined by n times n minus 1 over 2 inequalities, which are encoded in this table. So we have n times n minus 1 over 2 coordinates, and they are arranged into a table. So we have n minus 1 coordinates in the first row, n minus 2 coordinates in the second row, and so on, and 1 coordinate in the n minus first row. And inequalities can be read from this table using the following rule. So whenever we have such a triangle, A, B, C, this just means that C is between A and B. So here we have n times n minus 1 over 2 inequalities. So we have 2 inequalities here, 2 inequalities here, and so on. So let me give, again, three-dimensional example. So this is the Gelfand-Tsetlin polytope for GL3. And for, so here we actually defined the whole family of polytopes parameterized by lambda 1, lambda 2, and so on, lambda n. And we assume that lambda 1, lambda 2, lambda n is a strictly increasing collection of integer numbers. So if we take minus 1, 0, 1, we will get this polytope. So you see that it's not simple. It has a vertex where 4 edges meet. Polytope is called simple if at each vertex exactly d edges meet, where d is the dimension of the polytope. And this one is not simple. So in particular, if we assign a toric variety to such a polytope, it will be singular. And why it is natural to consider Gelfand-Tsetlin polytope in connection with Fleck varieties? Well, because integer points inside this polytope parameterize a basis in the irreducible representation of GLN. And the irreducible representation of GLN can be realized as spaces of global sections for line bundles on the Fleck variety. So line bundles on the Fleck variety correspond to irreducible representation of GLN. And later I will formulate some results which also relate Gelfand-Tsetlin polytopes to Newton-Akunkov bodies. Okay, and to relate this picture to the talk of Evgeny yesterday, let me also mention pipe dreams. So faces of Gelfand-Tsetlin polytope can be, certain faces of Gelfand-Tsetlin polytope can be identified with pipe dreams. Namely, we should consider faces that contain the lowest vertex. And lowest, by lowest vertex, I mean the lowest vertex with respect to the sum of coordinates. So here I have a certain height function, which is just the sum of coordinates. So the lowest vertex is this one. And I consider all faces that contain the lowest vertex, and they can be encoded by the diagrams. We get a face when one of the inequalities is replaced by an equality. So for instance, inequality that x is greater than or equal to lambda 1 can be replaced by equality. If we have this equality in our face, we put plus here. So we have 2 by 2 table, and we put pluses or empty spaces. And this is related to pipe dreams. I cannot draw such beautiful pictures as Evgeny, but if you replace each plus with a cross and empty space with an elbow joint and connect this with pipes in a unique possible way, then you will get a pipe dream. So it's just a lazy way of encoding a pipe dream, this table. But it's exactly the same thing. Okay, here are some examples. So the polytope itself is encoded by an empty table because we only have inequalities, we don't have any equations. Then this back left face is encoded by this table, so it's given by equation lambda 1 is equal to x. Then we have this left front face. It is encoded by equation y is equal to lambda 2. And finally, well, these are not all faces that contain the lowest vertex, just some of them. And the vertical edge that contain the lowest vertex is encoded by the table with 2 pluses. Okay, so the question how to represent Schubert cycles by faces of this polytope. And it turns out that in general it's not possible to represent a Schubert cycle, Schubert's variety, by a single face. So what do we want? We want to find a face such that it is in some sense a Newton-Akunkov polytope for a given Schubert variety. In particular, that means that the volume of this face gives the degree of a Schubert variety. And actually, more precisely, we will have that the number of integer points in this face is equal to the to the dimension of the space of global section of a line bundle restricted, of a line bundle on the Fleck variety restricted to the Schubert variety. But it turns out that it's not possible to find a single face with this property. But it is always possible to find a union of faces with this property. So we consider the union of faces as, it's not a polytope, but still can be regarded as generalized Newton-Okounkov polytope. Because we still can count its volume as a sum of volumes of all faces, and the number of integer points. Just count the integer points in this union of faces.
Valentina, is it exactly those faces that give the same monomial, as Evgeny explained yesterday? So different pipe dreams can give rise to the same monomial. So is it exactly those?
Yes, these are pipe dreams with the same permutation. Yes.
No.
Pipe dreams with the same permutation. No.
The face is represented by union of all. The Schubert cycle with permutation W is represented by the union of all faces whose pipe dreams have permutation W. That's the precise statement.
Okay.
Yeah, somehow for mysterious reason, the same pipe dreams parameterize monomials in a Schubert polynomial. But I don't know of any direct connection between these two statements. It's just combinatorial similarity.
There should be one, but we don't know.
Yeah. Okay, so when I say that we want to represent Schubert's variety by faces, I allow unions of faces as well. Because if we don't allow them, then the answer is no. But if we do allow them, then yes. Every Schubert's variety can be represented by union of faces. And the way one can think about this is the follows. So we have our Gelfand-Settler polytope, and now we try to take the Newton-Okounkov polytope of a Schubert subvariety. For instance, for this Schubert subvariety, we get a trapezoid, and now we try to realize this trapezoid as a face in the Gelfand-Settler polytope. And here we are successful. There is this back face, which is exactly this trapezoid. And now we take the Newton-Okounkov body for the other Schubert subvariety of codimension 1, and we get another trapezoid, but this one cannot be realized as a face. But if we fold it like this, then it can be realized as a union of faces. So I'm going to describe a general, explicit general algorithm how you should fold Newton-Okounkov polytopes of Schubert subvarieties so that they fit inside polytopes for Fleck varieties. That's the main purpose of my talk.
Sorry, Valentina, which valuation are you using?
Here I'm just talking, this is an example, so here I'm talking about Gelfand-Settler polytopes. You mean here when I...
You said it's a Newton-Okounkov body, right?
Yes, these are just, these two Schubert varieties, they are toric. So here it's not so important which valuation to use, so you just, these are Hirsebruch surfaces, so you just get trapezoids with any valuation. Okay, and just one word why it might be useful. In our joint work with Evgeny Smirnov and Vladan Timorin, we developed Schubert calculus in terms of Gelfand-Settler polytopes. And we believe that this is the most positive approach to computing structure constants for the cohomology of the Fleck varieties. Because when you intersect faces, you always get faces with positive coefficients. When you intersect, when you multiply to Schubert polynomials, some monomials can cancel. But here there are no cancellations, so you just intersect transferred faces and you get faces with positive coefficients. So here is some example. So suppose I want to multiply two Schubert cycles. That means that I should intersect this face and the union of these faces. And when I intersect them, I get this edge and this edge. So, and these two edges correspond to one-dimensional Schubert subvarieties. Okay, so let me just list some results about Fleck varieties and Gelfand-Settler polytopes. So I think the first person to consider relation between Schubert varieties and faces of Gelfand-Settler polytopes was Mikhail Kogan. In his thesis, he related Schubert varieties to preimages of pipe dreams, to preimages of faces corresponding to pipe dreams in the Gelfand-Settler polytope under a certain moment map. And then Mikhail Kogan and Ezra Miller used work of Alan Knudsen and Ezra Miller and constructed degenerations of Schubert varieties to reducible toric varieties. So Gelfand-Settler polytope can be considered as a polytope of a singular toric variety. and then unions of its faces corresponds to the unions of toric subvarieties in this toric variety. And it's possible to degenerate Schubert variety to this reducible toric variety. And then Kumars-Cave gave a unified description of cohomology rings of toric varieties and flag varieties using ideas of Khovansky and Pukhlikov. So he used volume polynomial of Gelfand-Sedlin polytopes. And this description made possible to do Schubert calculus. And in our joint work with Evgeny and Vladlen, we found presentations of Schubert cycles in terms of faces. And actually for each Schubert cycle we have different presentations, so we can always intersect faces transversally. Okay, so now my question is it possible to extend this to arbitrary flag varieties? So from now on, let G be an arbitrary connected reductive group, and X is the variety of complete flags for G. So how to represent Newton-Okounkov polytopes of Schubert subvarieties by faces, unions of faces of a single polytope. And what polytope should we take? So there are many candidates for this polytope. First of all, there are string polytopes, then constructed by Bernstein, Zerevitsky, and Litterman. Then there are Newton-Okounkov polytopes of flag varieties, and some of them were computed by Kumars and Dave Anderson. And finally, there are polytopes that I constructed using convex geometric divided difference operators, and this is a completely elementary construction, and in some cases it also gives Newton-Okounkov polytopes of flag varieties, but for different valuations, and I will say more about this in a couple of minutes. Okay, so I am in my talk I am going to use these divided difference operators polytopes, and my main tool will be geometric mitosis. So it's a convex geometric counterpart of Demazure operators from representation theory. And so this was just a motivation, and now I will give a completely elementary construction. Yeah, but just one more word about polytopes. So all these polytopes that I mentioned, they depend on the choice of a reduced decomposition of the longest permutation of the longest element in the while group. So let W0 be the longest element in the while group. So for instance, for symmetric group, it's the permutation which just takes 1 to n, 2 to n minus 1, and so on. And fix a reduced decomposition of the longest element. That means that no cancellations are possible. So the length is the minimal possible. Okay, then with this decomposition, one can associate a string polytope. And Kumars showed that these string polytopes coincide with Newton-Okounkov polytopes for flag variety if we choose the highest order term valuation associated with the flag of translated Schubert varieties. And the Schubert varieties correspond to terminal subwords in this decomposition. So we take such a flag, and then it gives a coordinate system on the flag variety. And if you have coordinates, you have valuation, and then you can apply this general construction of Newton-Okounkov polytopes. For instance, for GLN and this decomposition, one gets the classical Gelfand-Sedlin polytopes, which are partial cases of string polytopes. Okay, and one more result that I should mention is by Jason Miller. So it's in my talk I mentioned two different Millers. So he proved that Newton-Okounkov polytopes of Schubert varieties can be represented by union of faces of string polytopes, but this is just an existence result. So he shows that such faces exist, but he cannot describe them combinatorially or just. It's impossible to say which faces we should take. And explicit descriptions of such faces are known in the case of GLN for the Gelfand-Sedlin polytope, so for this decomposition. And in the case of SP4, this is diploma of a student of Dmitry Timashov, Masha Ilyukhina. So she did it for string polytope corresponding to this reduced decomposition. So this is symplectic string polytope. So it's an interesting question whether one can get explicit description of such faces for other groups and other choices of reduced decomposition. Okay, so now I come to the main part of my talk, the elementary part. So I will use ideas of Knudsen and Miller, who invented this combinatorial mitosis, and this is a purely combinatorial procedure which produces pipe dreams. So suppose you know all pipe dreams with permutation W, and you want to get all pipe dreams with permutation SIW, and we assume that the length of SIW is less than the length of W. Then there is explicit combinatorial algorithm what you should do, which crosses you should remove, which crosses you should move, and so on. So it's simple combinatorial procedure. And we noticed that basic steps of this procedure, they admit geometric realization in terms of parallelepipeds. And this realization preserves, sort of respects the action of Demazure operators. So I will say more about this in a minute. And now when we have these basic steps, we can replace gate von Zetten polytope by arbitrary polytope constructed by divided difference operators, and apply these basic steps now in a different combinatorial setting. So, and that's how we get geometric mitosis for arbitrary reductive groups. So this is the program, and now I'm going to explain it in more detail. So now you can forget everything I said before, and I give a very elementary definition of mitosis on parallelepipeds. So let P be a coordinate parallelepiped. That means that it's given by equations that each coordinate is between some numbers. So it's the simplest possible parallelepiped you can imagine. So its edges are parallel to coordinate axis. And define essential edges of P as edges given by these equations. So it means that x1 and xi minus 1 are fixed, xi is a free coordinate, and xi plus 1 and xn are also fixed. And we also require that coordinates before the free one, they are equal to mu i's, and coordinates after the free coordinate are equal to nu i's. So if we consider all essential edges, they form a path, continuous path, going from the lowest vertex to the highest vertex. And this is the path in three-dimensional case. So we always go, first we go along xn, then we go along xn minus 1, then along xn minus 2, and so on until we come to the highest vertex. So this is, the picture shows coordinate parallelepiped in R3 and its essential edges. Okay, now we define mitosis, and mitosis assigns to every face of pi, mitosis assigns a collection of faces dimension 1 greater. So suppose we are given a face gamma, how to construct the set M of gamma. So first we should find the minimal k such that gamma is contained in hyperplanes xi is equal to mu I for all I greater than k. So for instance, if gamma is not contained in the hyperplane xn is equal to mu n, then mitosis is empty. And if it is contained, we see whether it is contained in the next hyperplane and so on until we find the minimal k such that it is not contained in this hyperplane. And we also require that nu I is not equal to mu I for at least one I greater than k. Otherwise, our parallelepiped is just degenerate and is too, otherwise gamma is too degenerate to have mitosis. Okay, so we choose such gamma, and if no such gamma exists, then mitosis is empty. So that means that our face just dies without any offsprings. Okay, and now suppose that k exists, then we have isomorphism. Rn is isomorphic to rk times rn minus k, so it's just given by coordinates. And then under this isomorphism, our parallelepiped is the product of two smaller parallelepipeds, one sitting in rk and the other in n minus k. And our face is the product of two faces, but this face of P double prime is just a vertex because of this condition. So it's a vertex mu k plus 1, so on mu n. So basically, we have to apply mitosis to a vertex, and we don't care about this gamma prime. And if we have just a vertex, then mitosis of this vertex is just a set of essential edges. So Now to get the general definition, we take all essential edges in P double prime and multiply them by this phase gamma prime. So mitosis only affects coordinates with numbers greater than k, with indices greater than k. Okay, so if, I already said, if gamma is just the lowest vertex, then mitosis of this vertex is the set of essential edges. And this construction has a geometric meaning, well, kind of representation theoretic meaning. So if we take a sum of formal exponentials over integer points of gamma and apply certain Demazure operator, then we will get the sum of formal exponentials over all faces in M of gamma. And that's the motivation for such a definition. But maybe it's a too advanced word, Demazure operator, for this. It's basically the sum of geometric progression formula, nothing else. So it's very easy to show that this definition respects Demazure operators. Okay, and there is an interesting byproduct of this construction. Namely, it gives a realization of a simplex as a cubic complex. So because I think this part of my talk is closer to toric topology than anything else, so let me give an example. So here we have so this three-dimensional example. So we have a tetrahedron, and we want to add extra vertices and edges so that it becomes a cube. And here you can see that we added two vertices, and these are exactly essential edges of parallelepiped. So we would like to consider this set, the union of faces in this set, as a single face of a simplex. And this realization is minimal in the following sense. So here we introduced just two edges. Of course, we had to introduce 4 vertices because cube has 8 vertices and tetrahedron has only 4 vertices. And I talked to Taraspanov whether this realization of a simplex as a cubic complex was known. It seems to be new. And it's different from barycentric subdivision, which also give realization of a simplex as a cubic complex. Because with barycentric subdivision, in this case, you have to add 3 edges. So this subdivision is more minimal. Okay, so now what is the relation with pipe dreams? If instead of faces we consider their diagrams defined as follows. So if face is given by equation x1 is equal to mu1, we give plus, we put plus in this cell of the table. So we have 2 times n table, and we put pluses or leave cells empty using these rules. So for instance, and it is allowed to have 2 pluses in the same column. This just means that mu1 is equal to nu1. So our parallelepiped is not of full dimension. Okay, so for instance, in this example, we have a 3-dimensional parallelepiped in R4, and its vertex given by this equation is encoded by the following table. And these 2 pluses mean that our parallelepiped is not of dimension 4, but of dimension 3. And then mitosis of this face consists of 2 edges represented by this table. And if you remember combinatorial definition of mitosis of Knudsen-Miller, you will see that here we have exactly the same procedure. Okay, so what it has to do with Gelfand-Zetlin polytopes or more general polytopes for other reductive groups? Here's the connection. So let us first look at the Gelfand-Zetlin polytope. So you see that it has n-1 different fibrations by coordinate parallelepipeds. Namely, suppose I fixed all coordinates except for the coordinates, say, in the second row. Then I will get a section of my Gelfand-Zetlin polytope, which is a parallelepiped. Because if you look at the inequalities, you will see that each coordinate in the second row is between 2 numbers. So that means that we have n-1 different fibrations, and fibrations corresponding to the ith row produces a parallelepiped of dimension n minus I in general. That means that we have n-1 different mitosis operations corresponding to different choice of parallelepipeds. For instance, in 3-dimensional case, we will have 2 operations, M1 and M2. And if we apply, and now these operations can be applied in the same way as divided difference operators in Schubert calculus. So if I want to get phases corresponding to given Schubert cycle, I decompose its permutation into simple reflections and just apply the corresponding mitosis operations. So I start from the vertex, from the lowest vertex of my polytope. I apply M2. So I get this table, which is this edge. Then I apply M1. And this is the most interesting case because I get two tables. So I get two phases. And finally, I apply M2. And one of these tables just dies without offsprings. And the other produces the whole polytope. OK, so this is well known. And now let me show you a new example, namely mitosis in type C. So let us consider the group sp4. And then the corresponding divided difference operator is given by these inequalities. There are 8 inequalities. So we have 4 coordinates, x, y, z, t. So this is a polytope in 4-dimensional space. And we have 8 inequalities. And I showed that these polytopes also coincide with Newton-Okounkov polytopes, but for the lowest order term valuation. And it's associated to the same flag of translated Schubert varieties as for Kummer's result, but we take the lowest order term valuation instead of the highest order term valuation. And from the geometric viewpoint, it's more natural because lowest order term valuation is like taking the order of a pole of your function along a hypersurface. And these polytopes are different from string polytopes because one can easily compute they have 11 vertices, while string polytopes associated with either this decomposition or this one, there are only 2 of them in this case, they all have 12 vertices. So these polytopes are combinatorially different. But they can also be realized as Newton-Okounkov polytopes for certain natural geometric valuations on flag varieties. Okay, and one can also see that this polytope admits 2 different fibrations by rectangles. Namely, we can fix z and t, and then x and y will satisfy, x and y will lie inside a coordinate rectangle. Or we can fix x and y, and then z and t will lie in the coordinate rectangle. So that means that we have 2 mitosis operations on faces. And again, we only consider faces that contain the lowest vertex. The lowest vertex in this case is just the origin. So we remove all non-homogeneous inequalities and only consider homogeneous inequalities. So this one, this one, this one, and this one. And again, the equalities that define faces can be encoded by tables. And here, these tables are different from tables for GL3. So I call them skew pipe dreams. And the rule is as follows. So we put plus here if x is equal to 0, and, well, the same for other 3. So it's written here. OK, and what are the Schubert varieties in this case? So the full flag variety for sp4 consists of isotropic flags. That means that we take a line in the plane in 3 space in C4, but we have extra conditions that our symplectic form vanishes on V2, and V1 and V3 are orthogonal. So V3 is the orthogonal complement to V1 under this form. That means that V3 is completely defined by V1, so we can just remove it. And if we take projectivization, again, we have a point inside the line. Sorry, there should be P3 here. This is a misprint. So we have a point inside the line inside P3, and with extra condition that L is an isotropic line. So again, we can represent Schubert cycles by prescribing dimensions of intersections with a fixed flag. And here are the pictures. So this is 0-dimensional Schubert cycle, Schubert variety. So that means that we have a point inside a line, inside a plane which I fixed, and our flag just coincides with the point inside the line. Then we can move a point inside the line, or we can move the line around the point. And then if we move everything in all possible ways, we will get 8 Schubert cycles. I haven't drawn here the 8th one. The 8th one is a whole flag variety. So, for instance, this one means that we have only one condition, that our moving line intersects the fixed line. That's the condition on this flag. And here we have the condition that our moving point lies inside the fixed line. Okay, so how to get the corresponding union of faces? So we just apply mitosis. We have two mitosis operations. This is our lowest vertex. We can apply M1, M2, M1, M2. This is easier, and we just get the whole polytope. But if we first apply M2, and then M1, then M2, then M1, we'll get more complicated tables. So here we get 2 tables, and here we get 3 tables. So this corresponds to, so we first apply M2, M1, M2. That means that we got S2, S1, S2. So if we take Schubert variety S2, S1, S2, then its Newton-Okounkov polytope can be realized as the union of these 3 facets of this symplectic polytope, symplectic 4-dimensional polytope. Okay, thank you.